Welcome to our distributed machine learning project. We'll be scaling linear regression with the parameter server architecture. So the study is a study of when distributed machine learning helps and when it does not help. So the contents of this slideshow, we're going to find the introduction where it outlines the problem statement and the motivation. We're going to have the system setup next, the methodology, then the results, then challenges and solutions, then reflections. So now, why distribute machine learning? So modern data sets and models outgrow what a single machine can handle. There are certain challenges that we come across, and we listed four: memory ceiling, data sets exceed RAM on a single laptop, long wall clock time, hours to display for training what should take minutes. Then we have the single point failure. One crashed process loses all progress. Then wasted hardware, idle CPUs across the lab go unused. Then our hypothesis is that splitting training data across 3 community laptops and aggregating gradients via a central server should reduce training time without sacrificing accuracy. So the project goals and scope. In scope, we implement parameter server architecture from scratch. Then we train linear regression on the height weight data sets, which contains 25,000 records. Then compare single machine baseline versus 3 worker distributed. Then we measure the training time. We use the MSC, and also we check the scaling efficiency. Then we document failure nodes and recovery behavior. Then out of scope, we are not using GPUs for accelerating the process. We are only using CPUs for fair comparison, and also we are not going to use the asynchronous SGT approach. We're only using the synchronous gradient averaging. Then projection fault tolerance, it's out of our scope, and also model beyond the linear regressions, and also cloud deployment. So the software stack. On the software stack, the applications of the single machine.py, the parameter server.py, which is the Python files that contain the code that run the data set and go through the data set. So the RPC layer, we are using the gRPC protocol control buffers, which are within the parameter server. Then the numerics that we are using is NumPy, scikit-learn, and also the runtime is Python 3.10 on a Windows 10 or 11 machine. But with our system setup, the laptops are Windows 11. Then this is the network topology. We see that the worker 1 is connected to the server, worker 2, worker 1 to the server, and worker 2 to the server. Then this is the algorithm linear regression with SGT,
which will be the synchronized gradient average. Well, we'll be focusing on the linear regression model, where we'll be predicting the weight of a person based on the height. Where, like, we can see that this symbol, which is estimated y, it determines the weight of a person. Also, this one, the w, determines the height of a person, which will be our independent variable, and b, which will be our intercept. They will follow a linear regression model. Moving towards the MSE, on our results we'll be finding a variable called MSE. In statistics, it's called a mean square error, where, like, when we'll be interpreting the result, we will find that on average the difference between the observed value and the estimated value is this much. Now continue to the second slide, which is our data partitioning. How we'll be partitioning data on each and every devices, or should I say workers.
So here we have a live demo of the parameter server cross-platform training model, where we're training our linear regression model. So as you can see here, this is the main worker, which is a Linux-based system, and then this side we have a Windows-based system, which is our second worker. and here we have our another Windows-based system, which is another worker. So here on the main node, we have started our parameter server by first enabling a hotspot on this laptop, from which these two laptops can connect and have a communication. So now, as you can see, every 200 iterations there is a monitor that monitors the weight and the weights that are currently given to have a prediction model. So then here we're going to go to our live dashboard. As you can see, we have a live dashboard that will monitor the current iteration and the current loss after every iteration that we have within the training session. When we have stopped the training, our intercept, our bias will be displayed here, and then our slope will be displayed here, which is going to be our height coefficient, which from there we are going to use to do what? To predict the weight based off of an imported height. So this is our training as of right now. It is still continuing. Our data set is 25,000 records, which have been partitioned across 3 devices, as we have said before within the slides. So now we are going to demonstrate the single machine. As you've seen the distributed one, we are going to stop the parameter server, and then we are going to write Python 3 single underscore machine .py to run the script that will train based off of one single server. So as you can see, it is writing, then it has the results are saved. The results are saved in a comparison. For a single machine, here it is, the single machine loss training curve. The results are saved here across all platforms once it has been done. So these are the prediction. The prediction says that for a height of 70 inches, the weight would be approximately 34.4 pounds. We are using pounds and not kilograms.
So these are our results after running the 3 distributed machine. Then distribution lost. This are our findings. That's the finding. So we found out that the single machine finished in 37 milliseconds, whereas the distributor took about 6.1 seconds. The data set is too small to amortize communication cost. So you can see that this one the single machine took about 0.037 seconds, and then the distributor, which had 3 workers, took about 6.132 seconds. Then on the MEC, as in the previous slide, it was mentioned that it is to calculate
the mean square error.
The mean square error. We found that on the single machine, the result is 0.748 versus the 0.75, which is on the distributed. Now this math is right. Then the lesson that we took away is that distributing a 200 kilobyte data set over the network costs more than it saves. Communication has a fixed cost flow that distribution only beats when compute exceeds it. So now this is the performance comparison. Now we can see that the 0.037 is for the single machine, and on the orange bar we have the distributed part, which has 3 workers. Then this is the final test of the MSC. Then the convergence is preserved. You can see that these values are not far away from each other. Then the single one, and now this is the distributed one. So now we're gonna answer the question here, why distributed is lost, because it's going against our hypothesis. We're expecting the distributed system to be faster than the single machine. So now we see that the crossover happens at 5 million iterations. So that's where the distributed machine starts to compute. I mean, it starts to dominate the single machine, since the single machine can't fit. I mean, the data is, the more it runs, it can't fit in the RAM. So now the single machine starts to slow down. Then the distributed one, they start to dominate. So now we go to the challenges and solutions. So the real distributed system problems were encountered, and this is how we addressed each. So on the communication part, we have the gRPC overhead dominated compute. Now the problem was that on 25,000 rows, compute per iteration is 0.05 milliseconds, but each gRPC round trip cost 5 milliseconds. So distribution made things 165 times slower. So the solution is that we implemented is that we diagnosed it via timing breakdown, which confirms the theory. So the distribution only pays off when compute is greater than communication. So now we check the heterogeneous hardware part. The problem is that synchronous SGD waits for the slowest worker. Our i3 laptop gated every iteration, idling the Ryzens. Then the solution and the lessons learned is that synchronous protocols need homogeneous hardware and or async or backup worker schemes. Now, a worker can crash mid-iteration. So this problem is that the server blocked indefinitely waiting for an unresponsive worker, which is a classic straggler or failure issue. So the solution for this was that a heartbeat plus timeout, server continues with N1 workers and rebalances on the next reconnect. So then again, we have the imbalanced partitions. Now the problem is that we initially faced that initially partitioned by IP hash, uneven shared sizes, fast worker died waiting. Then so the solution is that we switch to equal size sequential partitions in the preprocessed data.py, which is a Python file. Then the lesson learned from all of this is that distributed has a cost floor. So communication is fixed cost, distribute only one computer per step, RPC latency. So we got negative results. It's not the results we expected, but there are still results. So our 1% speed up is a textbook demonstration of why workload size matters. So we found out then that convergence does not equal speed. It's not equal to speed. So distributed got the same as MAC. The math becomes correct. But this becomes a problem of, it becomes a system overhead issue, not the connection issue. So hardware heterogeneity hurts as well, that synchronous SDD waits for the slowest node. Then we found that's where we said that the i3 gated every iteration. So so the profile before optimizing that we assumed compute was slow. Measurement showed it was 100% gRPC marshalling. So we also outlined the real world implications. So what our toy parameter server tells us about about production in distributed machine learning is that architecture does matter. Same architecture, larger scale. Industry systems that use PyTorch data parallelism and TensorFlow parameter server strategy use the same conceptual model, just with hundreds of workers and specialized hardware. Then we also have the strangler problems persist. Even Google and Meta use the techniques like backup workers and the gradient compression to mitigate the same bottleneck we hit at 3 workers. So again, we look at the scale is that the right tool for the right scale. Out of our 25K raw workloads was too small to distribute. Real ML system distribute when the data set exceeds a single machine's memory, typically gigabytes to terabytes. So, and also the reliability is that fault tolerance is a system property. Production frameworks integrate checking points, retries, and elastic scaling. Features any team building distributed machine learning must plan for from day one. So this is all that we got, and this were our findings, and this is